Good evening. Good evening. Thank you for coming out tonight. I'm seeing a lot of new faces this evening and a lot of faces I haven't seen for a while, so I'm very excited to have everyone here. I'm Dave Farina, AELC Club President. We've got some other folks. Tom Lugar in the back is our club treasurer. Lane Davis, right hand Lane, is our vice president. So if you're looking for one of our officers at some point, here we are. For those of you who are new, I just want to give you some basics of how the club operates and the types of things that we do. And on our webpage, you'll see that there is an agenda for upcoming dates. Of course, this is tonight's meeting. Next week, we will be having one of our last Star Watches of the year. We have a total of 3 more Star Watches, one each month, and we always choose either a Friday or a Saturday for the Star Watch, and that decision is made on either Wednesday or Thursday of that week. So either the 21st or 22nd, based on the weather forecast, we will make a call whether we're going to be doing a Friday night or a Saturday night Star Watch. This month's Star Watch is going to be held at the Lancaster Environmental Center. And if you're not familiar with where that is, I'll click a link here. You can do the same. And it'll take you to a Google map. So this Lancaster Environmental Center is a very nice location just south of Lancaster City. And you can actually get directions to here by plugging in your address in the sidebar. So once again, that's next Friday or Saturday, 23rd and 24th, starts at 8 p.m. The topics for this month are going to be Mars and Saturn, which are currently up in the southern sky. We're also going to be talking about 2 stars, which are Antares, also a southern star, and Alberia, which is directly overhead and slightly towards the west right now, as well as the Omega Nebula, the Andromeda Galaxy, and a number of other constellations that are in the sky. So we do these once a month for 9 months of the year, and then we go into hibernation. It's cold. We still do some stuff as a club, so if you were interested in joining our club, we are active both for the public as well as our own interests. So we are year-round. We have a meeting every month, and we are really excited that you're here tonight. Tonight, we'll be talking about black holes. So if you weren't aware of that already, we'll talk more about that in a moment. And each month we have one of our we're okay. Each month we have a club member, Rob Webb, who is up front here, who does this program called Observing with Webb. And we thank Rob for that. It's an excellent overview of what's up in the sky. And that can be found right here on our website under the Observing with Webb tab. So yes, we got it up. Good to go. Okay. So Rob's got a special announcement he'll be speaking about afterward. It's part of his video as well. So I'm very happy for Rob, and he'll explain more both in the video and afterward. So here we go for this month's Observing with Webb.
Observing with Webb for September of 2016, where armchair astronomers figure out what they're looking at, why it's so cool, and what they should check out next. So this year, September's bringing us 4 planets, another start to fall, and some very good news for the Pequot Valley Planetarium. And before I get into the planets, the events, and the constellations, I want to talk to you just a little bit about this good news, and I also have a special request. I've been running the Pequot Valley Planetarium coming up on 10 years now. And it was 40 years old when I started. So that means it's 50. It's old. It's starting to fail. So I decided to write a proposal and submit it, along with hundreds of other teachers, to the Farmers Insurance Thank America's Teachers Dream Big Grant. And we were one of the 15 finalists, which is super exciting. I was surprised, I was happy, it was great. But here's the thing, I don't get that money yet because they only picked the top 6. And the way that they pick the top 6 is public voting. It has nothing to do with the proposal itself, and it's all to do with public voting. They're going to put all 15 up on a website. So just look for farmers.com/Thank America's Teachers. I'll have some links and stuff and more efficient stuff with that later. But if you just search Farmers, Thank America's Teachers, in October you will be able to see that and vote. Now it is September right now, but in October you can vote once every single day in October. That's 31 votes for the planetarium. So that's what I'm looking for. The top 6 votes. The top 6 proposals, you each get $100,000 to use for their proposal. And this is where I'm asking you a favor. Can you please vote for the planetarium in Peckler Valley? I will put some more information in the description box and other such things. Oh, that's right. What would we do with $100,000? Right? Really what we're looking for is, I want to establish a week-long summer STEM space camp that is free for all of the students in the district. Not that all of them would come, but it's free for all of the students in the district. Geared more for elementary, and then we have intermediate and secondary students being leaders of that. I also want to improve our curriculum to get more field trips and more expanded field trips. But perhaps more importantly is, we'll be able to replace the current lighting system because it's going away, it's burned out, there's very few bulbs left and they're not made anymore. I want to replace the bolted down seats, I want to replace them with cushioned, movable, stackable chairs. That'll open us up to many more opportunities for gathering there. Also, carpeting, and I want to replace the jerry-rigged sound system. And I also want to refurbish the Star Ball. What this does is it takes this aging and ailing planetarium, brings it back up to its former glory, so that we can then apply for more grants to get a bigger full dome video system, which would be amazing. But let's get it back up so that we can at least keep it running. It would be amazing. It's been a fixture in the community for 50 years. I really want to keep it going. This is what I need to keep it going. So please, I'll put more information in the description. Okay? All right. Let me move on to the planets for September. All right. So if we look at planets in September, in fact, let me look at like September 15th. Okay, that's a good average day. And what you're going to see is, let's first look at sunset in the west. Okay? You're going to see Venus off in the west. Okay? You just sort of tell with the W down there. Venus is going to be off in the west, and that's around sunset. It's only going to be about 10 degrees above the horizon at any point, but it will be very, very bright. You will be able to see it. You probably have about an hour to check it out. So that's one, that's around sunset. Also around sunset, and you kind of want to wait a little bit later, maybe until 8 o'clock, you're going to start seeing Mars and Saturn up in the south-southwest. Now what we notice about, Mars and Saturn is that to start out the month, center on the tails here. They start out the month about like this. Mars is about 6 degrees away or so. Then as the month goes by, I'm going to fast forward through the month, or through the days. What happens is Mars moves away from Saturn and into Aries, and they get much, much further away by the end of the month. In fact, there's a Goon Nebula up there on the 30th. But, throughout the month, Mars moves away to about 20 degrees from Saturn and into Aries by the end. And throughout the month, they're visible until about 10:30, 10 o'clock, something like that. That's about when they set. So if you want to see Mars and Saturn, make sure you get out there before 10 or 10:30, and you should be able to see them in the south, southwest. Okay? Now, that's it for the evening. Once it's 10:30, you won't see any planets. So if you were to stay up, you would just have to stay up, stay up, stay up, and you have to wait until the end of the month. In fact, I'm going to go to the, let's go 28th. You have to wait until the morning, okay? And look in the east in the morning. Ooh, a lot of stuff going on at night. And, oh, there we go. On the morning of the 29th, you'll be able to catch Mercury. And on, actually, a couple days before that, you'll be able to catch Mercury as well. Especially like the 24th and on, you can catch Mercury. But I would suggest looking on the 29th, if you have clear skies, because the moon, a very, very thin crescent moon, is going to be right next to Mercury. That's a great time to look because the moon's easier to find. You're going to need binoculars for this to find Mercury, but it will be bright. In fact, even Mercury is negative 0.5. That's pretty bright. The scale is opposite. The next closest bright star is, what did it say? Oh, 4, magnitude 4. Mercury is many, many, many times brighter. I know the numbers don't make sense, but look up the stellar magnitude scale sometime. But yeah, so if you look on September 29th or the end of the month, you might be able to catch Mercury off in the east in the morning before sunrise. You might have noticed I left out Jupiter. Why? Because even if you go September 1st and you look in the west around sunset, Jupiter's there, but it's so close to the sun and in a couple days it's gone. Don't worry, it'll be back in October for some morning stuff. All right, let's talk about some events. So let's go back to September 1st. And September 1st is the new moon. You can't see the moon, it's not up there. It's in between us and the sun. And in fact, if you live in Central Africa, you can see an annular eclipse, one of the ring of fire eclipses, where the moon doesn't cover up the entire surface of the sun. So you see a ring around the moon, but you don't see the corona. But again, that is in Africa, naturally. Then, if we wait until September 3rd, okay, you can actually see the moon and Venus, maybe Jupiter, but I don't think so. You can see the moon and Venus very low on the western horizon. You'll need binoculars for this, I think. The moon will be very, very, very thin. Venus will be bright. You should be able to catch them out there. But bring your binoculars for sunset on September 3rd. Now, then, if you were to follow the moon, you would notice throughout the month that it gets higher and higher in the sky and thicker until September 9th. September 9th is when you have the first quarter moon. The right half is lit up. You can see it from sunset, even before sunset, all the way to midnight, just about. And you might notice, get it to be nighttime here, the moon is actually close to Saturn and Mars. And in fact, let me back that up to the 7th. On the 7th, they make a pretty cool line where you have Mars on one side. Saturn is, I believe, about 7 degrees or 8 degrees away from Mars. Saturn and Mars separated by about 8 degrees. It's about 10 degrees away from the moon. So we make this neat little line. Remember, 10 degrees is your fist width held at arm's length. Okay? And then the next night, on September 8th, the moon is right above Saturn over here. So you'll be able to see those two together. And then on the 9th, the moon, Saturn, and Mars make a nice triangle in the night sky. All right. Now, if you have been paying attention and watching these before, you notice that the moon, day after day and night after night, will get thicker and thicker and actually move more toward the east until the 16th. What happens on the 16th? We'll just look at the moon. It's a full moon. Technically, there is a penumbral lunar eclipse, but that's only if you're in Europe, Africa, Asia, or the Pacific. I'm not. And the penumbral lunar eclipses are not that impressive. Can't really see much. So anyway, again, not much happens until the 22nd. What happens on the 22nd? nothing much in the sky, but it is the fall equinox, and that's when everywhere on Earth has approximately 12 hours a day and 12 hours a night, or 12 hours where the sun is above the horizon, 12 hours where it's below the horizon, just about. Now there is astronomically a much more specific and detailed way to calculate that. I'm not going to get into that. Just 12 hours a day, 12 hours a night. And it's the start of fall. Then the next night is the third quarter moon. Now remember, third quarter moon, you have to wait and wait and wait. There we go. Until, looks like 1:40 in the morning on the 23rd, somewhere around like 1 a.m., past 1 a.m. And you'll see the third quarter moon. Left half is lit up, and you can see it from about midnight, 1 a.m. into the morning. And it's hanging out right there in Orion, so that's a fun time to check that out because Orion's out there. The bow tie in the sky that's rising now, signifying to me that school is starting once again. Oh wait, it already started, but anyway, back to relevant things. September 29th. Let's fast forward there. As I said before, I believe, there you go, Mercury and the Moon are off in the east. Okay? That's a great time to look for them again because Mercury's hard to find, a very thin crescent moon is hard to find. We'll take your binoculars out and you can see both of them together. And then the new moon is on the 30th, the second new moon of the month. There might be a special name for that. I don't think there is, but yeah. Let me, sorry I'm rushing through this a bit today because I had that little announcement in the beginning and got to pick up my kids soon. So last thing here is constellations. Let's say we look straight up, so I'm going to point to the zenith and I'm going to do September 15th, setting for sunset. If you look straight up around sunset or maybe 8 o'clock, you should be able to see Lyra the Harp, which I really like. It's really pretty. You've got Cygnus the Swan over here as well, with the Milky Way running through it. If you have dark skies, you can actually see that. And then if you wait a little bit longer, Cygnus sort of goes through the zenith in particular, and then around midnight, Pegasus and Andromeda start coming into view. Pegasus is this great square, and Andromeda would be these two curves over here. And the Andromeda Galaxy is right here. You might be able to catch it with a telescope, or maybe even your naked eye if you have really dark skies. Now, if you're the type of person who looks up when you're taking out the trash in the morning because you forgot to do it the night before, if you look straight up in September, you should be able to find Perseus and Auriga and Taurus sort of hanging out in that area. And that leads you to Orion down here as well. That's all I'm going to do for this month with constellations. I would say go to skymaps.com and print off a sky map from there. That would be your best bet. And yes, please make sure that you check back in on YouTube or check my Twitter, Mr. WebPV, for updates on the Thank America's Teachers Grant. I'm really looking forward to getting a lot of votes for that. So if you keep tuned, I will let you know more and more, and it would just be amazing if we could do that. So anyway, I'd like to wish you very clear dark skies for the month of September.
All right, thank you once again. Folks, Rob has done 37 of these videos. He's been a friend of mine now for many years, and I want to give him a round of applause for making it to the top 15. Rob, do you have anything you'd like to add?
No, basically everything was in the video about what I want to do. It's just, this planetarium has been around for almost 50 years, and I'd like to keep it going. I just need to revamp it a little bit, and once I get this, I would like to move on and get a full dome digital, but that's later. This will at least keep us on our feet. What I'm going to do is, after our presentation, I'm going to have a laptop and an iPad set up here where you can just type in your email address, and that will sign you up for an email list that I manage, that you'll get an email reminder every day in October. I will be annoying, and don't take it personally.
After October, do we get daily emails?
No,
also?
you'll be done. I might send you like a, hey, we did a good job, but other than that, I won't spam you anymore after that.
When you get it, I want monthly. Here's the cool thing.
I will be updating you with a blog and everything.
That'd be great.
So I'll have that up here. Also, I have some lots of sheets if you just need to take some stuff home if you want to spread it around. I even have folders of sheets if you want to be an ambassador for me. I just made that name up right now. You can be my ambassador and hand it out to the places that you go to, your friends, your family. Everybody over the age of 18 can vote once a day, every day in October, and it would basically boost it back to where it's supposed to be. So,
Okay. Thank you, Rob.
thank you.
Going on that same idea, our AELC, we do our monthly mailing list as well. If you're interested in signing up for that, it's very similar to what Rob is talking about, but I don't do it once a day. I'm doing it once a month, and the idea here is to keep you up to date with what's happening with the club in terms of meetings just like this one, as well as our Star Watches and any other information that you might be interested in. And I definitely will be also adding Rob's information for the month of October. So if you can't find a link, or you're having a hard time finding a link for his planetarium grant, you'll have it via that as well. All right, so without further ado, we are going to be switching gears here momentarily. We have an amazing discussion tonight, and I do mean discussion, so if you have questions, please ask. Dr. Neil Brandt is here from Penn State main campus. So he's driven quite a while to get here, and I'm excited to have such a large and interested audience. So let's give a round of applause for Dr. Brandt.
Set up now?
Yes. While he's setting up, I know Dr. Brandt through an amazing program that they put together at Penn State for teachers through the years. I've taken 6 classes at Penn State through their teacher workshops, and Dr. Brandt's been one of the professors that's been there twice for me, and I've learned pretty much everything I know about black holes and cosmology, which is the study of the early universe, from Dr. Brandt and other professors out there. By the way, we have a number of other people from Penn State who are also interested in coming down to do these discussions with us. So please keep an eye on that calendar. I have another professor, Dr. Palma, coming in later in the year, early 2017. And he's going to be talking about his research in finding a small elliptical galaxy that has entered into our own Milky Way galaxy. This is research that he did as he was a graduate student getting his doctorate. So he'll be coming down early 2017, and I've got a number of other ones on the burner. So keep your eyes out. Lots of good things to come. Thank you, Dr. Franklin.
Thank you. And again, yeah, I am very happy to answer any questions you have. So feel free to stop me as I'm going along if you want me to explain something further or whatever. So today I'm going to talk to you about cosmic supermassive black hole growth. And I'm going to tell you about how we study that supermassive black hole growth using space observatories that work in the X-ray band. This subject has developed hugely over the past 17 years, owing to observations with the Chandra X-ray Observatory, shown here, and the European Space Agency's X-ray multi-mirror mission Newton. These have been the 2 trailblazer missions now, going for 17 years. They're still both working today, and hopefully we'll get another decade out of each of them. So these things were built to last. And I'll tell you a little bit more about how these operate later on. And this field, the field of cosmic X-ray surveys of supermassive black hole growth, has developed into a large industry now. In fact, there's now more than 600 substantial papers that have been published, scientific papers, from about 25 ongoing surveys, and hopefully some fraction of these papers are actually true. And I'll try to tell you about some of the stuff we actually believe is quite confidently true. I will not be able to be complete today, This is just going to be a broad overview of some of the highlights. I'm going to skim over a lot of complex details because I want this talk to be broadly accessible, but I do want to tell you that there's a tremendous amount of underlying work that you can go and read about if you want to learn in more detail. And if anybody really wants to dig in deep on this stuff, I can give you places after the talk where you can go to learn more. And so let's just jump into it then. So here's the outline for what I want to cover today. I'm going to move over here, I think that'll work better. So I'm going to start off by just telling you a little bit about active galactic nuclei and what those are. Those are accreting supermassive black holes in the centers of galaxies. That is, black holes that are swallowing up gas and dust and other materials, sometimes stars, in the central region of galaxies. And I'm going to present them from an X-ray point of view, because again, we're going to be talking about X-ray observations made with these satellites, okay, that we use to investigate this subject. I am then going to talk about the general utility of the X-ray surveys that we do to find AGNs. Why are X-rays a good thing to use? Why don't you use optical light or ultraviolet light or radio waves? Why are X-rays a good way to go for this subject? So I'll tell you about that. Then I'll give you some nice examples of the current X-ray surveys that have been done. And I will also present follow-up studies where once you actually can find all the X-ray sources, how do you investigate those sources further across the electromagnetic spectrum. I will then talk about some selected science results, just a few highlights of some particularly interesting discoveries. That is, what sort of intellectual payoff coming from all of this stuff. And then I'll end by talking about some future prospects for the field, where we hope to go in the coming decade or two with new missions or new observations. So that's the overall layout of where we're going. Let's just start off with this active galactic nuclei studies from an X-ray viewpoint. So first of all, what are active galactic nuclei? Well, when we look out into the distant universe, this is, I mean, we're looking beyond our own galaxy, out into the very distant universe, we see lots of galaxies out there, okay? And for the majority of those galaxies, like the two top panels here, the light that we see from those galaxies is just the sunlight from all the stars in those galaxies. So these galaxies are made up of billions of stars. Each of those stars is glowing the same way our sun is. You add up all that starlight, and that's what produces the composite light we're seeing from those galaxies. You study these galaxies spectrally in somewhat, and we know that the light that you see there produced basically by the summed up light of lots and lots of stars. That's what's making those the light. Now then, these active galactic nuclei, well, these are a minority group of galaxies, in round numbers about 10%. Okay? Where in addition to all that starlight, there's something else there. Something that's profoundly non-stellar. Okay? And what you see is in the nuclear region of the galaxy. So right at the galaxy center, you see a lot of activity. And here are two examples of these active galactic nuclei, where you have, in addition to all that starlight, here you can see the underlying starlight, which is still there. On top of that, you have this brilliant central point light source. Okay? And that's what we're going to be talking about today. Those are the active galactic nuclei. Okay? That's clear what an active galactic nucleus is, just observationally. We see these brilliant point light sources in the center of about 10% of galaxies. Now, what's going on to make this? Well, when we study the character of the radiation that comes out from these brilliant central sources, it's profoundly non-stellar. It's not star-like. Its spectrum is totally different than what you would expect from a star. So our best understanding, which I will tell you a lot more about in a bit, is that we believe that this radiation is being made by an accreting supermassive black hole. Okay? So you have a supermassive black hole sitting down in the central region of these galaxies, and that supermassive black hole is swallowing up gas and dust and stars, and in the process causing a lot of radiation to be produced. Now the black hole itself doesn't make the radiation, because nothing can come out of a black hole. So the black hole itself is not producing the radiation, but rather the material as it gets close to the black hole gets heated up to very high temperatures, and that's what produces the radiation. And I'll tell you a lot more about that shortly. Okay, so then what do I mean by supermassive black holes? Well, when I say supermassive black hole, I really mean it, okay? And I really mean supermassive. In terms of the masses, well, on the low end, for power these active galactic nuclei, we need a black hole with about 1 million times the mass of our sun. That's on the low end. The most powerful ones we see out into the distant universe, like the one seen here, for example, we believe have a much higher mass. The most extreme ones that we find have masses up to about 10 billion times the mass of our sun. These are truly enormous objects, a single object out there with a mass 10 million times the mass of our sun. These cause a tremendous amount of power to be produced. Okay? This accretion process on the black hole can produce, on the low end, about 1 billion times, and on the high end, up to about 10 trillion times the power that comes out from our sun. So you have this single accreting object that is outshining all the stars sometimes in the galaxy. You can see there's a galaxy down underneath the sword. But do you see the stars in this case? You don't really see them, right? And that's because they're being outshined by this other brilliant radiation source that beats out all the stars just such that you can't even see them. And you can see the same thing here. This thing is producing about as much light as all the stars in the entire galaxy put together. Yeah, go ahead.
Not in mass, but just in size. How much bigger is the black hole at the center of our galaxy than the sun?
Right, okay, good question. So the black hole, so first of all, he's alluding to something you may not know. We have a supermassive black hole in the center of our galaxy. Some of you probably know that. We have extensively studied it. Now, we don't live in an active galaxy, okay? We don't live in one of these. We live in one of these, but there's nevertheless is a supermassive black hole in the center of our galaxy, but it's hibernating right now. It's not accreting. So the black hole in the center of our galaxy has a mass of about 4 million times the mass of the sun. That's its mass. Now, in terms of its physical size, remember a black hole is very compact for its mass. It's only about 10 times the actual radius of the sun. So it's not that big. It's not a physically enormous object because black holes have an enormous density to them. And so even though they have a tremendous mass, they physically aren't that large. Does that answer your question? Yeah, okay.
How big did you say again relative to our sun?
About 10 times the radius of our sun in terms of its physical radius. So it's not wildly bigger than the sun in terms of its physical size, but it's vastly more massive. It's about 4 million times the mass. That makes sense? So, and that comes about due to very high density associated with the black hole. Okay, so, and these active galactic nuclei, this is going to be the main focus of what we're going to talk about today, okay? Because this is the main source population that we see in the X-ray surveys that we do with Chandra and XMM. In terms of the total number of objects we see when we look out in the universe, in the X-rays, and in terms of the total amount of power we're receiving from the universe, those supermassive black holes dominate the signal. And so we're going to study that. That's going to be the emphasis about these supermassive black holes, both in terms of numbers of objects, in terms of total integrated power coming in. The black holes are what do it. Okay. So I want to just highlight a few other things about these active galaxies. They have a number of spectacular properties. One, as I just said, is they produce this tremendous amount of radiation. In addition, sometimes these active galaxies aren't content just to produce a tremendous amount of light. They also sometimes produce a tremendous amount of kinetic power. Here's a case where here you have an active galaxy sitting down in the center of a galaxy. The whole galaxy in this case is about that big. And there's an accreting supermassive black hole down in there. And this is a radio-optical montage where the sort of purple colors here are radio images, and the optical light is sort of the whitish stuff. Okay? And you can see that this source has these enormous radio structures sticking out of it that shoot all the way out of the entire galaxy and shoot out into intergalactic space. Okay? So sometimes these active galaxies energize these very powerful structures called jets that they shoot out at a substantial fraction of the speed of light into the intergalactic medium. That's another thing these active galaxies can do. And now I just want to sort of step back and ask, well, why should you care about active galaxies? I mean, why do you want to listen to some guy give a talk about active galaxies? I mean, why is it worth hearing about them? Well, there are three big reasons that I use when I have to write a proposal to NASA or something to ask them to give me some money, why I think this is worthwhile. Okay? And here they are. The first one is by studying these active galaxies, we are directly observing the growth of supermassive black holes over cosmic history. Okay, so what do I mean by that? Well, what is one of these active galaxies that I've told you about here? Well, it's a growing supermassive black hole. The power is being made as I'll tell you about in more detail, because matter is falling into the supermassive black hole. So as a kilogram of matter falls into the supermassive black hole, the black hole's mass grows by a kilogram. So the black hole is growing on account of that accretion process. And so these active galaxies, these are the manifestation of black hole growth in the universe. So if you want to understand how black holes have grown in the universe, you've got to study these active galaxies, because this is the way that black holes grow. That make sense? Okay. That's reason number one. Reason number two is that, as I've just alluded to, these growing supermassive black holes produce extreme physical conditions, and that these are among the most extreme environments we find in the universe. The black hole, as I'll tell you about in more detail shortly, produces a region of very strong gravity. It produces a region of relativistic motions. These jets that I've just shown you here, these shoot out at relativistic speeds for many active galaxies. Okay? So you're producing relativistic motions at a good fraction of the speed of light. Furthermore, you produce very hot plasmas in these regions. The gas and other material that gets close to the black hole gets heated to a tremendous temperature to produce that radiation. So you produce these extraordinary conditions that aren't easily studied in many other parts of the universe. That's reason number two. Reason number three, that I will tell you about near the end of the talk, and I will just sort of set you up for it now, is we now actually are coming to appreciate that these active galaxies are an essential part of typical massive galaxies. Okay? That is, these supermassive black holes are not just present in only 10% of galaxies. I told you back here that only about 10% of galaxies are active. If we go and study normal galaxies, like these two, or, as you mentioned, when we study our own galaxy, we find there's a supermassive black hole there too. So at one time in the past, our galaxy was an active galaxy. Okay? It no longer is, but at one time in the past it was. And so the point is that we believe that a supermassive black hole is a typical, essential part of a typical healthy galaxy. Okay? And moreover, we believe that these growing supermassive black holes have exerted feedback upon galaxies that shape how they grew, shape how the galaxies evolved. And how do they do that? Via things like winds, jets, and radiation that I'll tell you about later on in the presentation. Okay, so now, as I said, I'm going to present this stuff from an X-ray point of view, because I'm an X-ray astronomer, and we're going to use X-rays to study these things. Well, so how does that work? How are the X-rays made? Well, here is a schematic showing, and I actually drew this diagram myself on a piece of paper, okay, and then scanned it in and put it in the top. This is our best understanding of what we think one of these systems is like. So you have a supermassive black hole down in there, and in round numbers, as we've heard, these aren't physically enormous objects. These would be the size of the inner solar system in terms of physical size. And round, when you think about it, that's sort of the typical size you're talking about there. But it's surrounded by this disk of material that is slowly working its way inward. It's falling onto the supermassive black hole. And it's doing that owing to the black hole's very large gravity. And as the material moves in, it is accreted. Well, again, every time a kilogram of material is accreted, the black hole's mass grows by a kilogram. And that's what I mean by the black hole growth. Now, the X-ray emission that we observe from these active galactic nuclei is made from a structure a coronal type structure that I sketched up here, okay, that sits above the accretion disk. These blue curves that I've drawn up here are representing magnetic fields. They have very high temperature plasma associated with them that's heated up at temperatures of billions of Kelvin, to such high temperature that it produces X-ray emission. Okay. And this model that we have for the production of X-ray emission is actually motivated by studies of objects much closer to home, like the sun. Here are some beautiful X-ray images of the sun. Okay? And when we study the sun, in the X-ray band, you don't see just the simple disk that we're all familiar with. You see these enormous coronal structures sticking up above the surface of the sun. These are magnetic fields sticking out of the sun's surface, going way up high, and they're filled with very high temperature plasma. And here's another example down here. Okay, you see these beautiful coronal loops sticking up above the surface of the sun. Well, we think the same thing is happening to a much more extreme extent for these active galaxies. And moreover, we think that, like on the sun, these are dynamical structures. Here's a beautiful image showing these solar coronal loops of magnetic fields on the surface of the sun. And look at them change over time. You see them changing as the sun rotates, as the sunspots move around on the surface, as the magnetic fields reorient themselves. They change. Well, the same thing is happening here, but to a much greater degree. Because here, actually, this disk, I will tell you, in its inner parts is rotating around at nearly the speed of light. And so you get this type of thing playing out much, much more rapidly. And that causes the production of a tremendous amount of power. Yeah, go ahead.
Are you saying that the ionized gas and the plasma, when it's heated to a certain temperature,
Yeah.
produces the X-rays?
Produces X-rays.
Does that happen on the sun also?
The sun never, well, yeah, it does to a much lesser extent. And to sort of give you some context there, the solar corona, the gas that's producing this kind of emission, is gas that has a temperature of a few million Kelvin. A few million. Okay. The gas that I'm studying in these active galaxies has a temperature of a few billion Kelvin. So it's 1,000 times hotter. But it's the same type of physical process that's going on. And that's what causes the X-rays to be made. But just a much more extreme version of it. Does that make sense? Yeah. Okay, so that's what makes the X-ray. Okay. Fine. So that's active galaxies. That's X-ray emission from these active galaxies. And this is a more technical plot. Don't stress over it too much. I just want to sort of show you that what we astronomers get excited about, okay, are actual X-ray spectra. So what this is a plot showing X-ray energy along this axis and the amount of flux coming out at a given energy along this axis. And basically, we see X-ray emission running over a very broad band from down to about 0.1 keV up to about 100 keV. And to put that in context, over here I put a spectrum in the same units of a medical X-ray machine, like the one used in your doctor's office or your dentist's office, okay? And your doctor or dentist, when they make pictures of your bones or make pictures of your teeth, are using sort of 50 to 100 keV X-rays in round numbers. That's the kind of energy X-rays that are being used. And we actually are studying X-rays in that band. That corresponds to this band here. So we are studying medical energy X-rays, like the ones your doctor or dentist use, and also even lower energy X-rays. And we use them all together to study these things. Okay. And so Chandra and XMM-Newton, the ones I'm going to talk mostly about, actually cover this 0.3 to 10 keV band, so actually somewhat lower energy than medical X-rays, but they still have many of the positive aspects of medical X-rays that I'll tell you about. That makes sense? Again, this is a rather technical plot. Don't stress over it if you don't get all the technical details. All these labeled components aren't what's important here, so don't worry about those. It's just the fact that we get this very broad band explanation. Okay, I do want to highlight that a new mission, NuSTAR, has launched. Some of you may have heard of the NuSTAR mission. This is a much smaller NASA mission that I'm actually currently heavily involved in, and it is actually able to make higher energy X-ray observations, where Chandra and XMM, as I've just said, cover this part of the band. NuSTAR is now very nicely filling in the higher energy X-ray part of the band. And Chandra and XMM-Newton and NuSTAR together are very powerful when used in concert. So I want to now talk a little bit about why these X-ray AGN surveys are useful. Why are X-rays a good way to go? But before I go any further, I'm happy to take any questions about that section. If there's anything. Yeah, go ahead.
Sorry for
That's fine.
some complicated questions, but
No problem.
those high temperatures you're talking about,
Yeah.
I would think there'd be gamma radiation, not X-ray radiation. So is this a result of the extra gravity we're working with?
Okay, you get both. Here is the broad band that you get. For the typical temperatures that you can produce this plasma at, you get emission over a very broad band, starting down at about 0.1 keV and running up to a couple hundred keV. And whether you call a couple hundred keV photon a high energy X-ray or a low energy gamma ray is somewhat an arbitrary thing. Okay, but that's about the band pass over which we get it. You actually don't get emission at much higher energies than that typically, because there's a limit to how hot this plasma can be made. Yeah, go ahead.
You said the black hole in our galaxy had been active but was no
Yeah,
longer active.
that's right.
Do we think that's a cyclic phenomenon?
Yeah, we do. And we have good evidence from the studies I'm going to be telling you about that indeed these things are cyclic. Yeah, things turn on and off over time. And there may be a time in the distant future when our black hole will fire up again.
What does it mean to life on Earth?
It probably will not hurt life on Earth, just because it's a relatively, as supermassive black holes go, it's a relatively low mass one. If we had a billion solar mass black hole in our galaxy, it would be a different story, and that could kill life on Earth. But we're lucky. In fact, that may be a reason why we made the models we have. Okay. So anyway, so now I want to move on and talk about why these X-ray surveys are useful. Why do X-ray surveys? Why build these fancy missions that cost millions of dollars to do all this stuff? Well, I'm going to tell you some reasons why. First of all, we can go back to this point that I've already alluded to, and that is that, well, X-ray emission is penetrating. Okay, here is an X-ray image of someone's broken bone. This fellow here kept calling me an X-ray astrologer. Joke. And so, anyway, the point here is that X-rays are highly penetrating. Okay, that's also true. That's true in the doctor's office, the dentist's office. That's also true from X-rays from the distant universe. Okay, and here is that same spectrum that I showed you before. And again, this is a little technical, but all I'm doing is adding absorption to it. I'm adding a certain amount of absorption to it. How much? Well, that's what's shown by this number here. To give you an idea, a number of about 10 to the 23, that's about the column density, the amount of absorbing material in your hand. Okay. 10 to the 24 is about a column density for your chest. And so look at 10 to the 24. Where do the X-rays get through? You don't get low energy X-rays through, but the high energy X-rays get through. That's why the doctor has to use 50 or 100 kV X-rays to take pictures of your bones. Okay? Now, when we study sources in the distant universe, owing to the cosmological redshift, we can actually study these high energy X-rays, the Chandra and XMM. We get the penetrating power of them. So the point here is that X-ray emission is very penetrating. It has reduced absorption by it. And this is very important because we know that galaxies are filled with lots of gas and dust and other obscuring material that often blocks the optical and ultraviolet light from getting out. But the X-rays almost always get out. So they give us a unique way of honing in on where the black hole growth is occurring in obscured systems and in unobscured systems, whereas the optical and ultraviolet are very biased against many obscured systems. Okay, that's one point. Here's the second point. X-rays have very low dilution by host galaxy star light, and these two pictures show what I mean by that. These are two pictures of a nearby local active galactic nucleus. That's its name, this particular one. It doesn't really matter what its name is. Here's the optical picture. Here's the X-ray picture. Which one looks prettier? Which one looks prettier? I'm sure it's obvious. That one looks prettier, right? Okay, to me that one's prettier, but to all everyone else that one's prettier. Okay. Well, why is that? Well, the point here is in the optical, you have the emission from the growing black hole in the central region, but you also have the light from all the stars competing with the light from the black hole. Okay? In the X-rays, what do you see? You see a single point-like object down in the center and essentially nothing else. Now, I haven't done any tricks with the scaling of the pictures or anything. The point is that you only get strong X-ray emission like this from one of these growing supermassive black holes. All the stars don't produce enough X-ray emission to compete with that, and so they all drop out of the imaging, and all you see is the brilliant central source. Okay. And so the point here is that X-ray lets you home in on black hole light and only black hole light. They have very low dilution by other forms of radiation, in particular starlight from all the stars in the galaxy. Now, that's important in nearby galaxies like this. It's even more important in the distant universe. Okay? Here's a picture of the distant universe. Okay, there it is. This is the famous, iconic Hubble Deep Field. One of the most famous pictures in all of astronomy. I'm sure many of you know and love this picture. Okay. There's about 3,000 galaxies in this picture. Okay? The point is that when you study galaxies in the distant universe, like say, pick one, pick this little smudge there. Can you go in and spatially resolve that one very much? No. Maybe a little bit, but not so much. So the point is that when you study galaxies in the distant universe, you don't have the luxury that you have here. Here, if you want to study the black hole in the center of this galaxy, you can just go and make a cut out just the light from this central part, because you can image it. You can cut out the light from the center because you know that's where the black hole will be. You can only study that light. See that? In the distant universe, you don't have that luxury because you can't resolve it well enough. So essentially, you have the light from all the stars in the host galaxy competing with the black hole light. So you need, when studying the distant universe, as I do, a form of radiation that has very low dilution by that host galaxy starlight, and that's what X-rays do. And here's the X-ray image of the same patch of sky that you have over here. Here we have 3,000 optical sources, as I said, and I will tell you, in our very deep X-ray observations, we know of 21 X-ray sources in that field, most of which are active galactic nuclei. There they are. Those are where the growing supermassive black holes are in this particular field. So this is a heck of a lot easier way to go. You take an X-ray picture, it just shows you that's where the black hole growth is. Boom, you just have it. Here, it's like trying to find a needle in a haystack, because you've got 3,000 of them. Only 20 of them are actually the ones, 21 of them are the ones that actually have any growing black holes. You've got to sort through all 3,000 to figure out which ones do and which ones don't. It drives you crazy. Okay, the X-rays just say, this is where the black hole growth is. Boom, you go there, you have your answer. Yes?
Are the active nuclei about the same distance away?
No, these are at a wide range of distances. I'll show you more about that in a minute. Some of these are enormously distant. Speaking colloquially, they're out at the edge of the universe. Some of these are actually quite nearby. So they span an enormous range of distances. And I'll say a lot more about that later on. Okay. Okay, so that's the point here.
A few more
right.
questions in the back.
Oh, yeah, sorry. Go ahead.
What about this field that you've got only 1% of AGNs, where you said, I thought you said at the beginning of the presentation, it might have been 10%.
You're saying why did we only, why
Yeah,
is
like
it
less
only
than
1%?
Yeah.
It's because we are, even in these even in this quite deep observation, we're not detecting all of them here. I'm going to show you even deeper observations later on where we do get a higher fraction. Okay. So it's just due to the depth. Even in an observation like this, we're not getting everything. I can show you even deeper observations where we get much closer to getting everything. And I'm going to show you that in a little bit. Okay. Yeah, go ahead.
What causes the gases to heat up hotter than the sun?
Right. Why does that happen? It's the black hole gravity that does it. Okay, so the point is this. As gas gets in close to this black hole, this gas is orbiting around. So this is like a cross-sectional picture. The gas is orbiting around the black hole. As it moves in, getting very close to the black hole, it is moving at a tremendous velocity. It's moving at a good fraction of the speed of light. Okay? That gas has magnetic fields associated with it. Those magnetic fields are continually getting stretched and torn apart, and when those magnetic fields dump out their energy, they heat up the gas. That's what's doing. The same thing that happens on the sun. Again, my movie's not working, but here it is. So the same thing that happens here, the same thing that makes the solar corona hot, is what's making this gas hot. It's just here it's a much more extreme version of it. Because instead of the sun, where the sun rotates every 28 days, here you have gas that's rotating around a good fraction of the speed of light. That make sense? Yeah? I want to make sure I answered your question. Good? Okay, fine. Any other questions? Yeah, go ahead.
What is that rotational speed on average?
In terms of like how
How
long?
fast? I
Okay,
think I know, for instance, pulsars can be.
oh, you're right. Yeah, in this case, again, these systems are physically very large. So even going at the speed of light, it takes a while. But they can rotate around, it depends on the mass. They can rotate around once a day, once, or in lower masses, 10 times a day or 100 times a day. That's the kind of rate at which you do it. But that still corresponds to moving at a good fraction of the speed of light. Okay? You know, it's the same thing how light takes a while to travel around the inner solar system. Just because it's a physically big system. Yeah, go ahead.
You're talking about the size again.
Yeah.
Not the mass, but the size.
Yep.
Is that the event horizon, or is that actually the size of the black hole?
When I'm speaking of the size, like that, and when I'm drawing this black circle here, I'm speaking of the event horizon radius, although I'm not going to get into that technical aspect. But that's what I'm speaking
So
of.
the actual size is point light, but,
The event horizon radius is what matters for an observer like me. I care about what comes out, not the subtleties of what happens inside.
if you cared about what's inside,
Yeah.
is it a point?
It's a point. There's a point down in, there's a singularity point down in there surrounded by an event horizon. But we're not gonna talk about that too much here. You can get Stephen Hawking to come tell you about those.
We can Stephen Hawking here on behalf of.
Okay. Go ahead.
Does the disk rotate differentially?
Yes, it does.
Okay, is there any evidence of dark matter there?
There will be dark matter there. Is there evidence for it? No. There's no evidence for it because we can't observe it. But we certainly expect it to be there, but it will not, the dark matter tends, again, this is getting a little technical, but the dark matter tends not to clump down as well as the gas does. So in a region like this, the normal matter density will be higher than the dark matter density, just due to the fact that the normal matter can clump, whereas the dark matter is not interacting, so it doesn't clump so much. Yeah, you have a question?
I think we're good.
We're good, okay, fine, great. Okay, so that lays out, lays out some of that. Now, I've told you about the utility of X-ray surveys, we've done that. Now I want to tell you a little bit about the X-ray surveys that we actually do. Okay, so what are all these fancy observatories actually doing? Well, we spend a lot of time doing these X-ray surveys, and I want to tell you about that. So, well, I'll go back to Chandra and XMM, those nice pictures we had at the start of Chandra and XMM. Here are these nice pictures showing Chandra and XMM. There are X-ray mirrors located here that are able to bring the X-rays to a focus. So the X-rays come in this way, they are brought to a focus by a set of mirrors here. They travel along this tube, and they're brought to a focus down to the back of this tube. Okay? And the same thing here. Here there actually are 3 X-ray telescopes, there, and there. The X-rays are brought to a focus by a set of mirrors, they travel along this tube, and that's where they're brought to the focus, at the end of that tube. Sitting at the ends of these tubes are CCD cameras. They're not radically different than the CCD cameras that are in your cell phones. Okay? There are some real differences there. But they're CCD-based cameras. They have the same operating principles as the CCD cameras in your cell phones, except they detect X-rays. Okay? So they're built differently to be able to do X-rays, and that's what I'm going to show you here. These two things, these two pictures I'm showing you here, these two things, these are the CCD cameras sitting at the backs of those tubes. And this thing here is my best friend in the entire world. That's how I got my professor job at Penn State, was that thing. That's a $50 million CCD camera that people at Penn State spent 20 years building and getting launched. And then they brought me in to analyze the data. So I know that thing like the back of my hand. I've analyzed the data from that thing for the past 17 years. Okay, XMM-Newton similarly has one. Here are the CCD cameras on XMM-Newton. And this one is called the Advanced CCD Imaging Spectrometer, ACIS. This one is called the European Photon Imaging Camera. Okay, so that's what they are. And what do these things give you? Well, they give you very good angular resolution in the X-ray band, over a broad band pass, and over a quite good field of view. Now I'm going to tell you more about some of those things in a minute. And what this translates into is very great sensitivity. The deepest observations we now make with Chandra are between like 80 and 400 times the sensitivity of those we had from previous X-ray units. That's an enormous advance. We're doing something up to 400 times better than we could before, just due to the improvements in design of Chandra, both of the CCD cameras and of the entire imaging system from start to finish. Okay. Furthermore, they give you very good positions. They can actually measure the locations of the X-ray sources very precisely. And that's essential for mapping, for taking the X-ray sources and matching them to sources at other wavelengths so we can figure out what they are. And furthermore, they generate large samples. I'll show you this in a minute. We typically, in the surveys we do, we detect hundreds to thousands of sources that let us do powerful statistical studies of what the source population is like. So here are my 2 favorite surveys. These are the Chandra deep fields. These are the deepest extragalactic observations that have ever been made in the X-ray band. Okay. This one is a 2 million second observation, and this one, as of earlier this year, we have now pushed to 7 million seconds of observation. That's a long time, okay? You put that in round numbers there, you're talking about something like, well, more than 70 days. So this has been more than 70 days of exposure they've used on Chandra to get these observations. And to give you an idea of the sizes of these fields, each of these fields is about 60% the size of the full moon on the sky. So each one of them is 60% the size of the full moon. This one, obviously, is in the north. That one's in the south. And all these little blips you're seeing in those images, those are the growing supermassive black holes that we're detecting. The majority of these little blips are the growing supermassive black holes, as detected in the X-ray band. In this case, we've detected about 1,055 of them in the entire field. And in this one, we have about 755 of them. And you'll notice that they're colored. They're colored because we can actually measure the energies of the X-rays as well. And so the colors are showing you the spectral character of the X-ray, which is one way we diagnose the nature of the sources. Okay. And again, as I've said, most of these are the active galactic nuclei that I care so much about. Most of these are growing supermassive black holes. These are the best images that people have of black hole growth in the distant universe. Okay. And sort of scale that up. Again, I told you, these are a lot of sources in a rather small part of the sky. If you scale up the density of sources that we find in the entire sky, that's about 1 billion. So if you survey the entire sky, the sensitivity we do here, you'd have about 1 billion supermassive black holes across the entire sky. That's the sort of numbers we're talking about. So there's a lot of them out there. Any questions about these pictures? Because I'm going to show you more examples of those in a minute. So it's good to go through and sort of answer any questions on these two. Yeah, go ahead.
Yeah, on the one on the left, there's a bit of color on the lower left-hand side.
Yeah, that's right. Yeah, it's because of the way, it's a technical artifact. It's not physical. It's just due to background subtraction issues leading to some spatial gradients down there.
And the ones on the outside, they look bigger than the ones in the middle.
Oh, good. Yes, good question. Yeah, absolutely. Right. Yeah, that's a good question. So he's pointing out the fact the ones down here look very point-like, and the ones out here look blotchy. And that's because the imaging quality of the telescope gets worse as you go off axis. So actually, they look more impressive out there, don't they? But the data is actually much better down in there. And I'll show you some central images of the central parts of the image. Yeah, but that's why these look more impressive, but the data is actually much better down in there. Yeah, go ahead.
Well, kind of two questions.
Yep.
Are there any lenses in this telescope? And is that mirror like a conical?
Right, no lenses. Okay, no lenses. No lenses. The imaging system is to bring X-rays to a focus. You actually use a rather different technique than, say, your bathroom mirror. Because you shine X-rays on your bathroom mirror, those penetrate into the mirror and stay there. Okay? The only way you can bring X-rays to a focus is actually to graze them off of a metallic surface. And so it's almost like skipping a stone off water.
So it's a conical?
It's a little technical, but the formal design is called a Wolter design. It uses a combination of a paraboloidal surface and a hyperboloidal surface. So each X-ray as it comes into the satellite is first reflected off a paraboloid and then is reflected off a hyperboloid. And the combination of the scattering off the paraboloid and the hyperboloid is what is able to bring it to a focus. And if you want to know more, you can learn X-ray off. Okay, that's how it works. Yeah, go ahead.
This million second cover, is that a standard recognized unit of measurement for exposure? 1 million seconds?
Well, it is for me. Most Chandra observations, I'll tell you, most Chandra observations are much shorter than this. A typical observation with Chandra is about 40 kiloseconds. So what does that mean practically? Well, in a day, there's 86 kiloseconds. So a typical Chandra observation is about half a day. These are, among all Chandra observations, these are by far the longest. Because if you want to study the distant universe really, really well, this is the kind of exposure that you require.
We're in the kilosecond range.
Well, these are in the megasecond range.
Well, those are.
These are mega. Typical observations like 40 kiloseconds in round numbers. Your typical observation is like half a day with Chandra. These are off scale. That's what we call the deep field. I need deep. I mean, these are very, very long. Get very sensitive data. That's what the deep there means. Yeah.
Just trying to bring in a sense of For instance, the Hubble Deep Field, there was quite a controversy among the scientists involved as to where to point the telescope for something this long. I mean, you're dedicating millions and millions of dollars towards one location.
Right.
How did you make a choice like this? What's the thing you would look for?
Yeah, I'm going to show you that in just a minute.
Okay.
I have the answer. The answer, I'll just tell you briefly, is we chose these regions of sky that have the best data, not only at the X-rays, but across the electromagnetic spectrum. These are two favored regions of sky. One in the north, one in the south. So the best multi-wavelength facilities, either the northern hemisphere or the southern hemisphere, whenever they want to do a deep survey, want to spend a lot of time doing a deep survey, they pick these patches of sky. So these are not only have the best X-ray data, they have the best data in the ultraviolet, in the optical, in the infrared, in the submillimeter, in the radio. Across their spectrum, these are the best fields. Because we can use all that data together to figure out things better than any single wavelength alone. That's how we pick them, yeah.
Do those fields overlap with either any of the Hubble?
Yeah, they do. Yeah, they do, that's right. Yeah, the Hubble Ultra Deep Field sits down in the middle of this one, for example. That's right. That's how, one way we picked it.
Half an hour or so, just so you're knowing how long.
Fine, half an hour right now, that's
Yeah.
fine, yeah, keep going. I think we're doing okay. Okay, so, right, I want to go through, I'm going to show you another nice example. So these are examples of, again, narrow sky region, very, very long observations. That's one way to do a survey. That's not the only way to do a survey. There's other good ways to do surveys too. Another approach, which other people have taken, is to not go as sensitive as these, but to cover a much larger region of sky. People do that as well. Here's an example. This is the famous Cosmos field. Okay? Here they didn't get nearly as long an observation as you asked. Here the typical observation depth is about 70 kiloseconds. So that's somewhat less than a day. But instead of covering a region that's only 60% the size of the moon, like we did here, they're covering 2 square degrees. Okay? And you get lots and lots of sources by covering those very wide fields for lower sensitivity. In this case, they have 1,887 sources. Again, most of those are growing black holes. Okay, so what we then do to figure out things about black hole growth in the universe is we combine together the information we get from the ultra deep fields with these fields and with all the other fields we can do to get a complete picture of black hole growth. And this is a technical plot, which I won't go into as to that, but you get the idea. Okay, so then to answer your question a little further about why did we pick these regions? Well, we picked these regions because, again, they have the best coverage at all wavelengths, as I already said. Here is what I mean by that. The Hubble Space Telescope has surveyed the central parts of these fields, about the central third, to enormous depths. Some of you may have heard of the famous Goods fields. The Goods field north sits in the middle of the Chandra Deep Field north, the Goods field south sits in the middle of the Chandra Deep Field south. So Hubble has spent an enormous amount of time in these fields. And that's great, because that lets us go and study the galaxy morphologies for these growing black holes. Here in the infrared, the largest ground-based telescopes on Earth have obtained very deep observations in the optical and in the near infrared. Here's a near infrared image that's taken with the AELC telescope in Chile. Here are our observations with Spitzer, NASA's great observatory in the infrared, as an ultra-deep imaging of these regions. In the submillimeter, ALMA now is getting fantastic data in the submillimeter band on these fields, letting us, as I'll talk about later on, discover galaxies in the process of formation. In the radio, the VLA telescopes located in New Mexico have obtained very deep radio observations over these same fields. And so that's why we pick these fields, and all this multi-wavelength data works great together. Because it lets us, from my point of view as an X-ray person, it lets us identify the X-ray sources, it lets us figure out what they are, it lets us measure properties of their host galaxies, like how massive are the galaxies in which black holes grow. How fast do stars form in the galaxies in which black holes grow, and so on. All those things are critically important for fully understanding the sources that we're detecting. And so that's why we chose these regions. And I also want to highlight the large amount of spectroscopic work that's been done, where people have used the largest optical telescopes on Earth Keck in Hawaii, the VLT in Chile, Subaru also in Hawaii, to get spectroscopy of all these X-ray sources, to actually measure redshifts and determine how far away these sources are. And that's been extremely important for just figuring out the nature. Until you know how far away these things are, it makes it very hard to figure out much about them. So over the past 17 years, there's been an enormous amount of progress using the multi-object spectrographs. And here I'm listing the names of the multi-object spectrographs on these telescopes that have been used to do the work. But this remains a challenge, because many of these X-ray sources are very faint. So this is still a bottleneck. And so some of you probably have heard of the fact that people aren't satisfied building these ones this big, and people now want to build 30-meter telescopes, or 50-meter telescopes, or even bigger telescopes. One of the reasons they want to do that is because we still have challenges finding and getting redshifts for the counterparts of all these X-ray sources. And so that's one driver of many. There's many drivers, but this is one big driver for the construction of even larger ground-based telescopes. Yes?
How difficult is it to get a redshift? You have
Hard.
galaxies moving away, you have one side going light speed, almost light speed away, and another half of it coming at you.
Well, the galaxy, remember, the galaxy itself is
And
not.
then if it's on an angle, you
Yeah.
know, the disk is
Yeah.
facing you.
Right, okay, so the galaxy is not rotating at anywhere near the speed of light. The region close to the black hole rotates near the speed of light. The galaxy, more broadly, is moving in a much more stately manner. And so that isn't a problem. What is a problem is the fact that these galaxies can be very faint. And I'll show you, going back to the Hubble Deep Field, or one of these examples, I'll just show you the good image here. I mean, we have X-ray sources in nice bright galaxies like this one, and we have X-ray sources in little splotchy specks like that, and we have X-ray sources in things so faint that you can't even see them on this picture that I've drawn here, and you can only detect them statistically by doing an image analysis on the data set. And so the challenge is many of these sources are so faint that even an 8-meter telescope has a hard time actually getting a spectrum to determine how far away it is. Yeah?
Can you just kind of explain a little more for the audience, the redshift concept? Just briefly.
Yeah, briefly. Okay, so the way, have some of you, many of you have heard of the concept of redshift. Okay, so people, owing to the expansion of the universe, galaxies are moving away from us in this grand cosmic expansion, okay? And we have worked out a relationship between how big the redshift of spectral lines is and how far away a galaxy is. That's the famous Hubble law that some of you may have heard of. I mean, you've heard of this guy Hubble, the guy the Hubble Space Telescope named after. Well, he must have done something pretty good, right? That's what Hubble figured out. He figured that out, and he figured out as a consequence the universe was expanding. And we used that Hubble relation, worked out by Hubble back in the 1930s, to get the distances. That's the basic idea of how we use spectrum and get the distances for these things. Okay.
I'm sorry.
Yeah, go ahead.
In other words, the farther away, the redder,
Correct.
if I recall.
That's correct.
Farther away.
The farther away, the more shifting of the light toward the red.
Right.
And we use spectral lines, where we know the characteristic barcode pattern that a galaxy should have, and we recognize that barcode pattern, but just shifted redward. And so it's like reading a barcode at the supermarket. That's essentially what we're doing, because we're doing it for galaxies.
And distance equals age. You're
Yeah,
looking
distance
back.
corresponds to age, that's right. When we look at very distant galaxies, we're looking at galaxies as they were long ago. Okay, so now I want to talk to you about some selected science results. Okay, so far I've been telling you a little bit about all the machinery. I've given you an introduction, I told you about doing the surveys, but what have we learned from all this stuff? What's the intellectual payoff of doing it? Well, there's a couple things. Okay, here's one of them. And this will be slightly technical in places, but it still should be quite clear, and I'll try to throw in a few jokes to make it happen. Okay, so one thing that we have known for a long time is that the population of active galaxies evolved strongly over the history of the universe. Okay. And here is a technical plot showing it. For those of you who are technical, showing redshift versus the density of luminous active galaxies. Here is the one that I teach to my Astro 100 grads at Penn State. Okay? And this one is actually more useful in some ways, okay, for being understandable. What it's showing is it's showing the density of luminous active galaxies the so-called quasars, which are the most luminous active galaxies, versus cosmic time, where the Big Bang is over here at time 0, and we are living today over at time 13.8 billion years over there. And what do you see about the population of quasars over cosmic history? It peaked a long time ago. That's right, it peaked a long time ago. Okay. And we have known this for a long time. We've known this since the 1970s. So this isn't new, but I'm telling you, we've known for a long time. Since the 1970s. What we have known since the 1970s, that luminous quasars peak strongly out at redshift of 2 to 3. Or speaking in another way, there was an era of the quasars. It was a few billion years after the Big Bang. Okay? And during that time, quasars were 1,000 times more common than they were earlier and than they are today. 1,000 times more common. So the population of quasars has evolved enormously over cosmic time. And if I could have picked any time in history when I would have wanted to live, I would have wanted to live there. Because I could have walked out of my backyard and looked up in the sky and seen quasars with my naked eyes. Okay, you could have walked out and looked up at the sky. You could see growing supermassive black holes with your eyes because they were so common. You would just see them out there. Okay. So the point here is that the population of quasars evolved tremendously. It's the same way that demographers of people on the Earth measure how the population of people changes over time in various countries. It's the same thing here. Quasars have had this enormous change over cosmic history. And this is both fascinating and depressing for someone like me. I mean, it's fascinating that it does it, but it's depressing because we missed the party. Okay, see what I mean? You know, the universe had this enormous party back here where there was tons of black hole growth, where there were tons of active galaxies, which again represent growing supermassive black holes. And we're there today, and we're just seeing a little bit of confetti that left on the floor. Okay? And when I tell this to my Penn State undergrad, they get very upset, because you all know Penn State undergrads don't like to miss a party. Okay? And so they tell me to get to work and fixing it. And I'm going to try to tell you how we actually fix this and we make the Penn State undergrads feel better. That'll be my next slide.
Are quasars and active galactic nuclei the same thing?
Yes. Quasars are the most luminous examples of them. They're the ones that are easy to study even when they're far away, just because they're so enormously powerful. That's why it was possible to study the quasars back in the 1970s. Okay. It took something like Chandra to take us to the next level of understanding, which is what I'm going to show you the next overhead. But right now, I just want to lay out the quasars very clearly. Does that make sense? Yes. Okay. Any other questions? Yeah, go ahead.
Yeah, I thought when you started this presentation that you were heading toward all the mass in the universe being in black holes. But it looks like because of this curve you just showed us that it will stop or nearly stop.
But I'm going to tell you it's not as bad as you think. Wait for my next slide. I'm going to reveal a fuller understanding of things that we have on account of Chandra. Right now, I'm just setting the stage. The next overhead is going to be the one that actually shows what we learn now.
So do you think we're headed toward?
Well, just let me do the next slide.
My question, I guess it sounds simple-minded, but
That's
you
fine.
said that you would have been looking up in the sky and seeing them.
Yeah.
What did you see? I mean, what is up there then?
But when we look out at the sky now and look up, you see stars. You see
Right.
stars in our galaxy.
Right.
The quasars today are so rare that you don't see them with your naked eye. It takes very deep telescopic observations to be able to see them.
But if you did see them, if they were so common, they were right over.
Back then they would have been. Yeah.
Well, what did it look like?
What do you see glowing? You see these fantastic blue glowing objects up in the sky. They would look star-like. They would look like stars, but they would actually be growing supermassive black holes.
Right, and it'd be common.
They would be common.
Wow.
That's right. They'd be 1,000 times more common than they are now. Plus, the fact the universe was smaller back then, which makes it even better. Okay?
Okay.
Yeah, go ahead.
Is there any way that spike could occur again?
It's probably not going to occur again. And that comes from understanding where the spike came from in the first place. And let's sort of guess. I mean, I'm sure people in this audience can guess the origin of this. Let's ask this. Why weren't there quasars right after the Big Bang? Why weren't there quasars 10 seconds after the Big Bang? What?
There was no mass.
So there was mass, but the mass hadn't concentrated down yet into galaxies. There weren't galaxies yet. It took a while. It took a while to build galaxies. And you need galaxies to be able to build black holes. So back here, the reason why there weren't quasars back then is because galaxies hadn't been built. But after you build galaxies, the quasars came in very fast thereafter. And does anybody want to guess what happened here? Why did they stop? Why do populations die off on Earth? Go ahead.
Run out of food.
Sucked up all there was to suck up.
That's right. They run out of food. They run out of food. They sucked up all the food. They had their feast. They ate up all the stuff in the center of galaxies, and there wasn't any more to eat. And so the black holes didn't go away. The black holes are still there, but it's just they declined in activity, so they're no longer around. Does that make sense? So that's the origin of that. And we've known that since the 70s. Okay. Now again, we're going to go back to trying to make the Penn State undergrads feel better. Okay? The point is that the quasars tell you this depressing story, that we missed a party. The universe had this huge party, we missed it, too bad for us. But the problem is, with this entire branch of study, until we had something like Chandra, is that we were only studying the quasars. These are the rare, one in a thousand most powerful examples of active galaxies. They do not tell us how most active galaxies evolve. That's what I'm going to tell you about what we figured out from Chandra. Okay, and that's what this slide means. This is a technical slide, a little technical, but it should be understandable. So now I'm showing this as a function of redshift. Redshift 0 is where we are today, and as you go in this direction, you're moving to greater and greater, more distant objects. So all these are great distances, okay? And what I've done in this plot, and here I'm showing number density again, and what I've done is I've color-coded these curves. These are the most powerful active galaxies we find now using Chandra-based X-ray surveys, where we can find all the active galaxies out there. These are somewhat less luminous, somewhat less luminous still, somewhat less luminous still, somewhat less luminous still. What do you see as you move to less and less luminous populations in terms of where they peak? Someone tell me what you see from that plot.
Closer to now.
They peak later and later in cosmic time, don't they? The most powerful objects, entirely consistent with what people have known since the 1970s, peak are creatures of the distant universe, as we know. But as you go to less and less luminous objects that you couldn't find before you had the Chandra surveys, as you go to these less and less luminous, we find they peak at later and later cosmic times. Okay? And that's the point. Lower luminosity active galaxies peak at later cosmic times. This is a remarkable thing for a number of reasons. First of all, it's totally anti-hierarchical. We normally think of structure of the universe starting small. You build some little things, the little things merge together and make a bigger thing. Those merge together and make a bigger thing still. So you start off small and go big, right? This is the opposite. The big things came first and the little things came later. And that's because you're moving through many generations, likely thousands of generations of quasars turning on and off, or active galaxies, turning on and off, on and off, on and off. And this is the superimposed pattern of all of those put together. So that's how you get an anti-hierarchical behavior. And the point is that unlike what you would have expected from the quasars, where the bulk of supermassive black hole power production is out of the redshift of 2 to 3, very distant, we think it's now more of the redshift of like 1 and 1.5. And the lower luminosity systems are peaking at even later redshifts still. And so the point here is that we didn't entirely miss the party. Okay? We didn't miss the party. The Penn State undergrads can feel better. Okay? The party just shifted to smaller and smaller scales. Okay? The huge sort of campus-wide parties indeed happen in the distant universe. But the smaller sort of frat house or sorority house parties are still happening today. And that makes the Penn State undergrad much happier. Go ahead.
Is that because as the universe expands, could it be?
I have to do this because I teach this to hundreds of Penn State undergrads.
As the universe expands, it takes longer for everything to get to it, to be sucked in?
I mean, why is this happening?
No, I'm saying, could it be happening so it takes longer for the material to get to the black hole because everything is getting bigger and bigger and bigger and bigger?
Yeah, we don't think that's the cause. We think the cause has to do with how galaxies use their gas. What do I mean by that? We think that the most massive systems, while they have more gas to start with, they use it much more flagrantly. and it gets gobbled up very quickly. Whereas the lower mass galaxies are much more stingy in how they hold on to their gas, and that lets the black hole activity occur later and later in cosmic time. And the technical reasons for that come with studying the technical subtleties of diagrams like this. Okay. That's the overall answer. Yeah, go ahead.
Stars also.
Stars behave that way as well, exactly. That's analogous to what stars do. It's not the same physics, but it's the same idea. You probably know that massive stars, even though they have more gas, live shorter lives than low-mass stars. Well, it's the same type of thing happening. It's because behind that, even though they have more stuff, they burn that material more flagrantly. And that's what makes them last less time than the low-mass stars. Well, it turns out galaxies and their supermassive black holes have a similar behavior to them. And that's what Chandra taught us. Okay, so that's one example of what we learned. So we act like demographers, census makers of black hole growth in the universe. Okay, the one yes, okay. So now I have to tell you about this point. Okay, so again, the point here is that, again, these curves represent the production of enormous numbers of black holes over cosmic time. While the black holes may shut off and no longer be active, well, the black hole itself doesn't go away. So you can ask the question, where are all these black holes? Where are they now? The same question we asked about movie stars and got the answer to recently in the new Star Wars movie. So where are they? Well, as I've already alluded to, we now know where they are. There are local galaxies around us today. You look at the center of our galaxy. The center of our galaxy is a 4 million solar mass black hole. That black hole had to be built. At one time in the past, we were in one of these systems. At some time in the past, we built our black hole. We once lived in an active galaxy. We no longer do. Okay, and this is the same thing in general. Here's the plot just showing examples of galaxies. Here's many galaxies. Here's one here. Here's the full image of the entire galaxy. That's a Hubble Space Telescope image of the very central region. This one has a 3 million solar mass black hole in it. Here's another one. Here's the galaxy. That's the central region. This one has a 20 million solar mass black hole in it. Here's another one. There's the galaxy. There's the central region. 200 million solar mass black hole. There it is. Here's an even bigger one. The 2 billion solar mass black hole. That's that big circle there. Okay? That's that one. What do you notice about the relation? Do you see a relation there?
They really start to blow up as they get heavier.
As they get heavier, sure. They get bigger as they get heavier, for sure. You notice any relation between the galaxy property and the black hole property? Well, do bigger galaxies have bigger black holes or smaller black holes? Bigger black holes. You can see that just from that diagram, and that holds more generally. And this is a remarkable thing, and I want to tell you about that. Okay. Here's what I want to tell you about. This is going to lead to the role of active galaxies in galaxy evolution. What you just noticed from that previous diagram holds more generally. And this is a truly amazing plot. It shows the mass of the black holes in centers of galaxies versus, in this case, the velocity dispersion of the stars in the galaxy's bulge. So we know the galaxies have bulges. Here are two famous galaxies. This one and 104, the famous Sombrero galaxy, that's the galaxy's bulge. We measure how the stars in that bulge move, which tell us essentially the mass of the bulge, and we find this amazing relation that I just showed you between the mass of a black hole in the center bulge of the galaxy and the mass of the galaxy bulge. Here's the correlation. It holds generally. This is an amazing thing because, again, as I've talked about, the black hole is a rather tiny object. It's only the size of the solar system. Whereas the bulge, well, this is the enormous bulge of the galaxy. I mean, in terms of relative scales, this is if you took the galaxy bulge to the size of the Earth, the black hole would be the size of a pebble. Yet somehow the entire bulge knows about that black hole. This is an amazing thing that we don't fully understand, and we are trying to understand right now. The thing that makes it very challenging to figure out is that we are essentially studying in this diagram, we are studying the remnants of things that were once great. What do I mean by that? Well, when you look at black holes, the black holes we're studying and measuring masses for all these galaxies are dead black holes. They're hibernating black holes that are no longer growing. They're not active systems anymore. Okay? So it's kind of like studying the bones of the dinosaurs. They were once great, now they're dead. It's very hard to figure out a whole lot about them just from the bones. Okay. Similarly, along this axis, when we study galaxy bulges, like this one, or like this here, M87, where the entire galaxy is a bulge, okay? These systems, especially the bulges, are dead systems, in the sense that they're no longer forming stars. You probably know the galaxy bulges don't form stars very much. Okay, so that's the challenge that we face in a diagram like this. It's hard to figure out where this beautiful relation came from, because black holes aren't growing anymore, the bulges aren't growing anymore, and so you're essentially studying dinosaur bones and trying to figure out things about the dinosaurs from them. Okay, what I want to do from these X-ray surveys, I want to go back to Jurassic Park, or now they call it Jurassic World, the rebranded movie, I guess. And I want to actually see directly the growth of the black holes and the growth of the galaxies, and we can do that. We can actually directly see these things together. And I want to tell you about our attempts to do that, and then I'll finish up. So I'm going to show you a movie now to sort of illustrate how this might have come about. That is, how did the relation between a black hole and a galaxy come about? How did the black hole, for example, influence a galaxy to shape it, set up this correlation? Well, here's a movie I'm going to show you. Moving to the next slide, I'm going to get you ready for it now. It's a movie made by a professor at Penn State, Eugene Lee. She's a theoretical astronomer. She runs massive computer simulations to try to work this stuff out. And what you're going to see is a movie, and here are some stills from the movie. And essentially, the intensity of the shot is showing the density of gas in the system. And the color shows the gas temperature, such that the purplish gas is nice and cold, and the yellow color gas is very hot. And these black circles in there, those are the black holes, the supermassive black holes in these systems. Okay? And you're going to see a pair of galaxies coming in and merging. You're going to see them firing up the active supermassive black hole and then blowing gas out of the galaxy. So I'm just going to let the movie run. So here it's running. We have galaxies, sets of galaxies that are merging to form a single large galaxy. There they're doing it. Okay? Galaxies continue to merge. There are more galaxies coming in and merging, forming a single large galaxy. Okay? The galaxy is merging, it's setting itself up. Soon you're going to see the black hole firing up and starting to drive a powerful high temperature outflow from the system. There it is. See all that high temperature gas being produced by the black hole? And see how that's pushing out the cold gas? There it's firing up, becoming very bright, pushing out all the cold gas from the system. We think that type of phenomenon may be responsible for setting up this relation between black holes and galaxies. Okay? You're essentially, in a system like this, driving out all the cold gas. That cold gas is essential to feed the black hole and to allow stars to form. And by driving out all that gas, you essentially truncate star formation and you truncate black hole growth. And if conditions are right, and do it in a synchronized way, you can set up this relation between black hole properties and galaxy properties. So that's what we're trying to do theoretically. Observationally, I'm very excited right now about combining sub-millimeter observation and X-ray observation. So in particular, I'm interested in X-ray studies of these famous sub-millimeter galaxies that some of you may have heard of. But these are not little galaxies less than a millimeter in size. These are galaxies detected by their strong sub-millimeter emission. Why are they strongly emitting in the sub-millimeter? Well, it's because they have tremendous bursts of star formation going on in them. These galaxies are forming stars at about 1,000 solar masses every year. That's about 1,000 times the rate our galaxy forms stars. Yet they're optically nondescript because they're heavily extincted by all the dust in the system. These galaxies have now been identified using telescopes like the James Clerk Maxwell telescope, which operated in Hawaii, and now ALMA, the Icon Large Millimeter Array, shown down here. And we find that these extremely powerfully star-forming galaxies are creatures of the distant universe. They typically exist at high redshifts of 1.5 to 3, where they're about 1,000 times more common than they are today. We have a few examples of such systems today, 2 examples are shown here, but they're much more common in the distant universe. Why are these exciting? Well, because we are seeing galaxies here building their bulges. Okay, I told you galaxy bulges are dead today, right? But they weren't always dead. In the past, galaxies had to build these things. These bulges just didn't spontaneously come into existence. They had to be built. Well, by observing these submillimeter galaxies, we are now actually finding galaxies in the process of building their bulges in the distant universe. We can actually see the bulge being manufactured, the submillimeter emission that you home in on then. So the question then is, well, given that we have this remarkable relation between bulges and black holes, can we see the black holes growing too? And the answer is, yeah, we actually think we can. We're making progress on that right now. And we're combining together data from ALMA and data from Chandra to do it. Here's a nice plot from some work that my group has done, showing here X-ray observations. This is the X-ray image. This is the corresponding ALMA image. So again, this shows you there's a galaxy there building its bulge. This image shows you, and there's a growing black hole there too. You see? Growing bulge, growing black hole. Here's another one. Growing bulge, growing black hole. Growing bulge, growing black hole. Growing bulge, growing black hole. We actually find that a high fraction of these bright submillimeter galaxies are X-ray detected in the very deep surveys we perform. They often show evidence for AGN activity, such that 20 to 35% of these systems, which is a very, very high fraction compared to galaxies as a whole, have growing supermassive black holes in them. So this suggests a very high duty cycle for black hole growth in forming bulges. Every time you have a galaxy that's building its bulge, you commonly see a growing supermassive black hole in there too. So we actually hope now that we are directly observing the formation of this connection between black hole growth and star formation rate. And we're trying to quantify this and understand it further right now. And I'm just going to end with a couple of future prospects. We still want to have some big unresolved questions. We want to push to the even more distant universe to understand how the first black holes came about. We want to understand better, as I just alluded to, how black holes and their galaxy populations, how their black holes and galaxy stellar populations evolve, and we want to understand how large-scale cosmic environments shape black hole growth. We hope to answer these questions. Chandra, as I told you about, is we're still working great. This plot here shows the state of health of all the major Chandra subsystems. The details don't matter. The most important thing is that our current estimates indicate that both Chandra and XMM-Newton can likely last until 2025 and perhaps beyond. Okay, so we have a good amount of time. We can hope to conduct many more surveys with Chandra and XMM. These things were built to last. Okay, again, they were launched in 1999 and 2000. They may well be going out in 2025. So these things will be long-lived missions. So we hope to conduct many more wonderful X-ray surveys to answer some of those questions. Furthermore, there's lots of new multi-wavelength data that will be coming from better radio telescopes. ALMA, as I already told you about, is producing great stuff. The James Webb Space Telescope will let us observe very distant galaxies in these fields. The Large Synoptic Survey Telescope will be surveying these fields to look at time variability aspects of the AGNs. We hope to use extremely large telescopes to get better spectra. All these things together, plus better X-ray data, will let us pin down this black hole growth even better. We also hope in the future to have even better X-ray surveyors. Soon, a mission called eRosita will launch. It should launch in 2017, and it will survey the entire sky much more sensitively than we have so far. It should detect something like 5 million growing supermassive black holes across the entire sky. That's one for every school kid in Pennsylvania or something. Each school kid can have a black hole. Furthermore, Athena, a large European mission with also substantial U.S. involvement, where I'm actually on the science working group for it, is expected to launch in 2028. That will let us conduct even more powerful surveys, and we have dreams of even more powerful instruments still. I'll wrap up there. Thank you very much. You asked a lot of great questions. I'm happy to answer any more if there's time.
Yeah, just let me just wrap up by saying I want to thank Dr. Brandt once again for coming from such a far distance and for the dedication that he puts in to do this type of work on nights and weekends and throughout the summer. Let's just give one more round of applause. Some new business cards that we've made here as a way to try to get the word out there. So if you know someone or would like one of the business cards for yourself, they have, there's 6 different options. They each have a different picture that one of the club members has taken through a telescope. Most of them are from Lane back there, so Lane will help you out. For our club members, if you wouldn't mind grabbing a handful, we've got a lot of these cards. We want to try to get them out to as many people as possible so that more people find out about this, this program that we're trying to continue to grow. So last bit, don't forget about Rob Webb and his planetarium. We've got lots of cool stuff. He'll be up front here. And Tom Lugar. Tom, raise your hand again one more time if you would. Tom is our treasurer, and if you're interested in joining AELC, please speak to him. Thank you and have a good evening. And if we have any questions.
Yeah, I'm happy to stick around and answer any questions one-on-one.
Thank you, folks.
Chandra next time. Yeah, they are. Let me tell you what I call them. Chandra. Way, way out. That's right. They're Chandra's over the cut 3.5 No, I pulled one out. I pulled this out, so I pulled it out.
Oh, I had the chairs.
Oh, yeah.
Relax.
So plasma generally
That's going to be quite something. It's going to be farther out. Wavelength. I was up at Star Party. I heard it a few years ago. And the speaker
we're seeing back in your mind.
Like
When humans first started walking in this tower,
actually take a spectrum.
and they're still there.
All those peaks and all those trees don't act at the time, right? They're still there. They're not sucking in more gas. That's how they, okay. That's why he makes the they have. In other words, he'll pick it out, look at extract, but they have to.
My question for is,
This guy,
planets are stars, planets and comets, you actually do video, when you take random video, and you're trying to make images of you, when you do that,
I have no shit. Every time I've been
you're going to take more than a few seconds to image, your image will start
edges hang
as you
down.
start tracking as well. Hey Logan, and I'm experiencing this myself, really good setup. My setup has a problem. If you're trying to do planetary though, you can take a video, you can use your camera cam for the video. For reasons that are very kind of counterintuitive, webcams actually and they sell webcams, they sell webcams, you can upgrade it.
This is what we do, and I did that for less than $100.
And then that video, you just take it on your computer and you use a program. And it takes all these frames, this one, and this one actually. And as a result, the atmosphere takes the best of those images. What we're doing is we're literally taking individual images, we're trying to align them properly, and then taking the worst ones and run them out. Use all that data to make one image out of it, and as a result, we get the entire So there are options for that. Yeah. Well, that's okay. The only thing you need to do is the video is even in your field of view, fairly narrow. Because this one with knobs. Well, what's interesting, when I drive on, it doesn't self-track. It doesn't self-track on the sky or on the space. So you're just going to need to sit there and you're going to watch the screen, either on your laptop or on the camera. And you're just going to watch where it is. And you just go with the knob. Keep the knob and keep it in view. And you should be able to get video. Yeah. And then if you're interested, once again, membership is $20 a year. So, you guys have to say, the government has he got it 3 years ago. And you guys down exactly what you're saying. Working. That's cool, man. As far as right. Good. Just taking a very high. Sure. Good. Keep in mind a telescope an image upside down. And you're going to see upside down.
Just let me know if you have any questions.
Back in Hawaii,
have a look at this.
Go in and check it out.
There's the NuSTAR. There are these great big stars.
Yeah, it's,
See, I don't see that we can see some of that stuff now.
yeah, so, okay.
Oh, so you already did that? Oh, you did that? Okay, cover. Thank you.
Well, it's time spent. It was never, it was not something I picked up myself, you know? I teach it now. I have provisions.
Okay, it's great.
And, all right, you're right, and now we're going to so you put as much time in it as I had to figure it out. It's not a. They know a lot of other things that I know. We each have our things.
Well, if you think of it, nothing's changed.
Everything's the same, address is all the same, email's all the same, I'm still getting everything. Address is all the same.
I was about to say, I recognize it, but I haven't seen it.
I don't ask that question. There's something, you ask me, I know it's around there.
Stuff gets in the way.
I don't know everything around there.
Tom, were there needs me to know telescope?
What's the question?
Riding in their ears.
I just was up Cherry Springs with during that Black Forest.
Very good day.
Folks, we do need to wrap up. The library is trying to close, so we can slowly make our way out. That'd be great. Thank you.
I've won every year except one time. I won something. I got it. Kansas was very distant.
They don't have any shade.